Oh, welcome back to MATLAB Programming for Engineers. So for the last few weeks, we've been doing simulations, essentially computing the solution to a differential equation from scratch by programming using the simplest possible algorithm. In the future, it's unlikely you will often actually do that because MATLAB has built-in solvers to do that for you much more efficiently using better, more accurate algorithms. So I'm going to give you an introduction to how to use the most commonly used of these solvers. It's called ODE 45. And don't worry much about what the 45 stands for. It just has to do with the specific type of solver. There are others that you can use as well. And the guidance from MathWorks generally is try ODE 45 first. If it doesn't work because you have a particularly difficult equation that you're trying to work on, what's called a mathematically stiff equation, then try the next one, which is called ODE 23. But it works exactly the same way. So we're talking about solvers for ordinary differential equations. And if you've had a differential equations course, you know that the way you solve a partial differential equation is by separating it into ordinary differential equations. So if you know how to solve an ODE, then you're halfway to being able to solve a PDE. What we're going to start with as an example is one of the simplest differential equations in the world, which is describing the charging of a capacitor. And so we have an RC circuit, and at some point we close the switch. Now this diagram doesn't show any switch, but let's say we turn on the voltage, and current flows into the capacitor until it charges up to this voltage, and then no more current flows. And this is something that can be solved exactly, but we're going to use it as an illustration of the solver technique in MATLAB. All right, so here's the differential equation that you get. If you've had basic circuit analysis, you can get this by Kirchhoff's voltage law, but it relates the derivative of the voltage across the capacitor to the voltage itself. Because as you may have learned in physics, the current through a capacitor depends on the derivative, the time derivative of the voltage across it. Well, the first step in setting this up so you can solve it in MATLAB is to solve it for the derivative. That is, you want to have some expression for dVc dt, or the more common way of writing it is Vc dot. A dot just means the time derivative. So if you were to solve this equation for Vc dot, this is what you get. All right, so you see this is a differential equation because you've got an equation that relates the derivative to the quantity itself. Now, how do you set this up in MATLAB? Well, the key is you have to write a function representing this quantity Vc dot. Yeah, that's what you have to provide to the solver. A function that tells it how to calculate the derivative given the quantity itself. All right, so let's set up some numerical parameters, the values for the resistance and capacitance, and the battery voltage, let's just say it's 1 volt. Then, of course, the other crucial thing in solving any differential equation is the initial condition. So we need to know what was the voltage on the capacitor when we started. And so initially, we'll say the capacitor was completely discharged, so the voltage was 0. All right, now here's the crucial step. This is just translating this equation into a function. And often it's convenient to use an anonymous function like this. Okay, so we need an equation for Vc dot or dV dt, whichever you want to call it. It's Vs minus Vc over Rc. Okay, Vs minus Vc over Rc. And I'm just defining that as an anonymous function. I'm choosing to call it dV dt. Now here's one thing that's a little strange, or at least looks a little strange. What's this t doing here? Well, when you're using the solvers, you always have to set up this function so that it takes the independent variable, which in this case is time, as one of the arguments. Even though, if you look at this expression, there's no t in it. If this equation does not explicitly depend on time, doesn't matter, you still have to put time as the first argument here. And then the other argument it takes is, of course, the voltage Vc. All right, so if we know Vc, then we can get dV dt as a function of time. Now, how do you use the solver? Well, like so. So it's called ODE 45. That's the one we're using. The first thing you pass it is a handle to the function that defines the derivative. Now, if you use an anonymous function, that is the handle. If you had done it as an external or local function, then you would have put an at here in front of the function name to turn it into a function handle. The second thing is the range of times over which you want to solve the equation. So I'm going to solve from 0 up to 5 milliseconds, just because from the numbers, I know that's a reasonable range to look at. And the third thing you have to give it is the initial condition, which, as I said earlier, is just the voltage is 0. All right, so that's what you provide to the solver: the derivative function, the range of times, the initial condition. And it gives you back two vectors: the time and the solution as a vector. Right? So we're solving for VC, the voltage across the capacitor, versus time. So that's what it's giving us. And then we can plot it. Right, so let's run this section. And you get this traditional charging curve for a capacitor, exponential charging. All right. So that's how you use ODE 45 for a simple first order differential equation. That is one that only has one derivative in it, only has the first derivative. A lot of the equations that you need to deal with are higher order. So let's do an example of that. So extending our circuits problem, let's say we add in an inductor. And now it's got two energy storage elements. Both the capacitor and the inductor can store energy. That's what makes it a second order system. If you were to write this as a single differential equation, the equation describing the circuit, it'll be a second order equation. You'll have a second derivative in it. Now, that's actually not what we do when we're using ODE 45. For our purposes, what we need is not a single second order differential equation. We need two first order differential equations. And we need an equation for the derivative of each of the quantities that represents energy storage in the system. Those are called state variables. Right? So there are two ways energy can be stored: in the voltage on the capacitor or in the current through the inductor. Or to get more down to the fundamental physics, it's in the electric field on the capacitor and the magnetic field in the inductor. Right? So the two state variables are going to be the current I and the capacitor voltage VC. So we want to solve our equations for the derivatives of those two quantities: I dot, which is di dt, and VC dot, just like before. And if you know how to analyze circuits, again, you apply Kirchhoff's rules, and this is what you'll get. Now, what do we do with these two equations? Well, now we need to set up something similar to what we had before, where we had the derivative equals some function of the quantities. But now we have two variables. What we do is put them into a vector. Right? So we think of it as solving for a vector that has both I dot and VC dot in it, which means the coefficient is going to be a matrix now. Right? So you take this pair of equations and you write it in matrix form like so. I dot VC dot equals, and you just pick out the coefficients. And so what's the coefficient in the first equation for the I term? It's minus R over L. So that goes there. What's the coefficient for the VC term? It's minus 1 over L. That goes there. And you look at the second equation. What's the coefficient for the I term? 1 over C. What's the coefficient for the VC term? Well, there is none, so it's 0. All right, but then there's one more thing. You also have a constant term in the first equation, Vs over L. And that has to get added as well. Okay, so you add a vector with the constant terms, which are, for the first equation is Vs over L, and the second equation, again, doesn't have any constant terms, so you just put a 0. All right, so this is the matrix way of writing this pair of equations. And now it's in a form that we can pass it to ODE to solve for us. So what we're going to do in terms of programming, we're going to think in terms of a variable x, capital X, which is the vector that contains I and VC. And that's what we're trying to solve for. So if you think of it that way, then this big matrix equation here can be written as x dot equals mx plus v, where v is this constant vector. All right, how do we translate that into code? Well, first we have to create this matrix M, right? And that's easy enough to do in MATLAB. And we create this vector V. All right, so there's creating the matrix M, there's creating the vector V. And just like before, we define a function to give us the derivative. dx dt equals mx plus v. And again, we're making it an anonymous function. Takes two inputs, the time, again, the independent variable, and then the variable x, okay, because that appears in this expression. And we pass that function to ODE 45, just like before. And so if you look at that, it almost looks like it could be a first order equation because we've just grouped everything together into this vector x. Right, we pass the function dx dt, specify the range of times. Turns out in this case, about 1 millisecond is going to be a good range. And then the initial condition. But now we have two variables, two state variables. Therefore, we have two initial conditions, and we lump them together into a vector. Okay, and the initial conditions were defined back here. So I'm starting out with no voltage and no current. So it's like there's a switch, and we just close the switch at t equals 0. Okay, and importantly, this has to be a column vector. Okay. All right, so we've passed it the derivative function, the range of times, the initial condition vector. We run it, and it'll solve for x and t, or solve for x versus t. All right, so there's the time vector. And notice x is now a matrix. Okay, each column of this matrix is the solution for one of the two variables. Just because of the way I wrote the equations, the order in which I wrote them, the first column is going to be I, the second column is going to be VC. Right, so I extract those, extract the two columns of the matrix and the individual individual vectors, and then I can plot them. And you see that's what it looks like. And this is a second order equation. I picked the number so that it's underdamped, which means it oscillates. And you can see the current and voltage oscillate, but out of phase with each other. All right, so that's how you solve a second order differential equation with ODE 45 by writing it as two first order differential equations and then putting it in matrix form. Let's do another example, which is a mechanics problem. This is actually a parachute simulation. We did something like this in some of the in-class examples. Now it talks about the first parachute exercise. We don't give that one as an assignment anymore, but it used to be the first exercise we would give on mechanics would be a parachutist. And we would use a linear drag model. You know, we ended up using the more realistic quadratic drag model, but we used to have people start out just using the simpler linear model. And I'm going to use that here because it's compatible with this matrix formulation. If we use the quadratic drag model, you can't write it in matrix form like this. So just to keep it simple, I'm going to use what's called Stokes drag, which is really only valid for very low Reynolds number. So it's probably not realistic to use it for a skydiver, but we're not going to worry about that. Okay. All right, so if you think in terms of a linear drag model, and we have just a skydiver, so he's constantly falling, his acceleration is going to be g minus kv. So the way we're setting up our coordinate system and handling the sign convention, g is a negative number here. I've said many times, you can use either convention you want. In this example, the convention I'm using is g is a negative number. And so really, even though it looks positive here, g is downward. And of course, the person is falling downward, which means the velocity is negative, which means the drag term is actually positive, so it's upward. And so it's not obvious from the equation, but The weight is downward, the drag is upward, just like it should be. All right, so that's the acceleration. Well, what is the acceleration? It's the time derivative of the velocity. So that's one of our two equations. Okay, so the velocity is going to be one of our state variables, and we've got an equation for its derivative here. V dot equals g minus kv. What's the other state variable? Just the altitude, the height, which we'll call y. And what's the equation for that? Well, just y dot equals v. All right, so those are our two first order differential equations. The second one is completely trivial, but we still need it. All right, so we put those into a vector like before, v dot y dot equals, and we write it in matrix form. Right? So you look at this pair of equations, pick out the coefficients, minus k, 0 because there's no y in this equation, 1, and 0 again because there's no y in this equation either. And then you add the constant term. Well, the first equation has a constant term of g. The second one doesn't have a constant term, so it's 0. Right? And then we translate that into MATLAB just like before. We put in the numerical parameters. Initial condition is 0 velocity at an altitude of 4,000 meters. Constant vector is just g and 0. Now, what's the matrix? Right, so we just translate this matrix, minus k0, 1, 0. dx dt. Right, so we want this to be an anonymous function. And remember, the first argument has to be the time. And the other argument is going to be the vector that contains the two variables, x. So I'm using the same trick I did in the previous example, where capital X represents this vector that has v and y in it. And then what's this equation? X dot equals mx plus, in this case I called it g, just like before. All right, so it looks just like the previous one, because all the details are lumped into this matrix in this vector. We call the solver, and we have to give it handle to the function, the range of times. Now, for starters, I'm just going to go 60 seconds, because the way this problem was formulated, it said that the parachute was deployed at 60 seconds. So there's a discontinuity there. Something changes midway through, and you have to think about how to handle that. Let me just solve it for the first 60 seconds first, and then we'll come back and think about that. And then the initial conditions, which I put into this vector x0. All right, and then we run it. Oops. It's just the old plots. There we go. All right, so there's the altitude or the height in blue and the velocity in red, and you can see it's hitting a terminal velocity. Right, at some point, the drag is just balancing the weight, and from that point on, he falls at constant velocity. All right, now what if we want to account for the parachute opening? Let me put a figure here so we can get rid of that old graph. Okay. All right, so now we want to account for the parachute opening at t equals 60 seconds. And the way this problem used to be formulated, we would say that when the parachute opens, this factor k increases by a factor of 10. All right, so how am I going to do that? Somehow in this equation, I need to say that at t equals 60 seconds, and from that point on, instead of k, we're going to have 10 times k. And what I'm going to do, I'm going to take this matrix explicitly and put it here. That's just going to make it easier for me to do this. And now instead of k, instead of just k, I'm going to have k times 1 plus 9 times t greater than 0. Or I'm sorry, greater than 60. All right, so logical expression is coming to our rescue here. We don't need an if statement. We can just say, if t is greater than 60, add 9 to this 1, which means we're going to be multiplying k by 10. All right, let's see if that works. And now I'm going to run this up to say 200 seconds. All right, there we go. Okay. Now you see at t equals 60 seconds, the parachute opens and he goes up to a much lower terminal velocity. And the slope of the y versus t curve drastically decreases. All right, so that's a way that MATLAB will do for you all the hard work that we've been making you do with these simulations. Just these few lines of code are running that whole simulation, just like you've been doing with the Euler method, but doing it more accurately. All right, so if you go to the exercise, there's a problem similar to this, but it's a solid mechanics problem. But a lot of the steps are pretty much the same. So you should be able to generalize it from this problem.